Okay, so far we've seen what the properties of a binary search tree is. In that, we see that the value of left child, that is here V2, will be smaller than V1 and V3 is greater than V1. Similarly, here V4 would be smaller than V2 and V5 is greater than V2. So now to search for a value in a binary search tree, we'll exploit this property and do it in login times. Okay, so let's see. So consider we had to search for V5 in this tree. So first we'll compare V5 with the root node, which is V5 here. So V5 is smaller than V1. We'll jump to the left subtree of V1. Here we'll again compare V5 with V2. V2 is smaller than V5. So we again jump to the right subtree of V2. Here we find V5. Okay, now let's see an example of how do we actually query in a binary search tree. Let's see here how do we search for 7. So we start from our root node, that is 12. We compare 7 with 12. We find that 7 is smaller than 12. So we jump to the left subtree of 12. Here we compare 7 with the root node of the left subtree, that is 5. So we find that 5 is smaller than 7. Then we jump to right subtree of 5. We compare 8 with 7, which is greater than 7. So we jump to the left subtree of 8. Here we successfully find 7 in the left subtree of 8. Next, let's see how do we prove that its time complexity is log n. N is number of nodes in the tree. Okay, so let's consider a tree . Here we have seen that once we compare a value with the root node of the tree, we simply discard the other subtree. So let us say that we are searching for V5 here. So the V5 will be smaller than V1, hence we'll jump to the left subtree of the binary search tree and the right side is discarded. Hence, this will be continued until we reach the required node, that is V5 here as a reef node. On the way, the number of steps that we took, this is equal to log base 2 of n, where n is the number of nodes, because at each step we see that the graph is divided into two parts. Hence, to query a binary search tree, we go through log n number of nodes. Yeah, so now we discuss the time complexity of searching in a binary search tree. So for an example, let's see, we'll search for V12 in this graph. So initially we have 15 nodes. Here at the first step, we'll compare V11 with V1. So since V11 is in the left subtree of V1, V11 is smaller than V1. We'll go here and we discard all these nodes. So now we are left with only n by 2 nodes. Next, we compare V11 with V2. Now since V11 is in the right subtree of V2, we'll go here in the right subtree of V2 and discard all these nodes. Now we are left with n by 4 elements. Again we will see that V11 is in the right subtree of V5. We go there and we get the value V11. So in this process we see in step 1 we reduced our search size by n by 2. In the next step we again reduced it by half, that is n by 4, and this keeps going on. So total number of steps required are nothing but log of base 2 of n. Hence, the time complexity of searching for a key in a binary search tree is order of log n. So now we have an exercise for you to evaluate on searching. The instructions are just click on the generate a random binary search tree button. Here the question is just enter the number of steps required to search for the node 70 in the given graph. So in this case the number of steps would be total of 3 steps. So if you enter your answer here and click on check answer, you will get the right answer. If you make any mistake, this will be evaluated to incorrect. If you want to see the solution, just click on the solution and it will go through the path that is to be traced to search for the node 70.